Hi everyone. Okay, so today I'm going to do a wee lesson on resistors in series and parallel circuits. So on the screen just now you should see a series circuit and a parallel circuit. So just do a wee recap about what that means and what we already know about series and parallel circuits. And then I'm going to use that PhET website again to see if we can notice what happens to the current when we add resistors in each of these ways, and what that must mean is happening to the overall resistance of that circuit using what we already know about the relationship between resistance and current from Ohm's law. Okay, so a series circuit. I know this is a series circuit because there's only one path for the current. So the current going around this circuit has to go through this 10 ohm resistor and has to go through this other 10 ohm resistor. This is a parallel circuit because at this point there's a choice for our charges coming around the circuit here. So the current's going to split and then we'll have that full current again coming around here. So that was the last piece of work you did, recognising that the total current in the parallel is equal to the sum of the current through each of the branches. For the ones I've got set up, you'd actually have the same current through each branch in this parallel circuit because they both have the same resistance. So we'll look at some examples with the same resistance and some with different resistances as well. Okay, so if we go to the PhET website now, I've just got a couple set up like this. Remember, you can pause the video, you can set them up yourself, have a play about, use the ammeter and see what you can find out yourselves, or you can just keep watching and watch with me. Okay, so here are our circuits set up here. So each of these is identical just now. It might not look identical, but if you look down the bottom half here, we've got an open switch. So this whole bottom section of the circuit may as well not be there. There's no path for the charges to flow, so the current is only, we only got current in that top half, the same as what we've got on the left-hand side. So each is just one resistor. If I show values, you'll see that there are 2 ohm resistors and a 6 volt supply. See that wee infinity sign down there? So the infinite resistance in that open switch. So we've got no current flowing down there. Okay, so I'm just going to add a second resistor to each of these circuits, but on the first one, I'm going to add it in series. So I'm going to add it in a way that means the current has to go through both 2 ohm resistors. And the second one, I'm going to add it in parallel, which means we've got that junction here, and you can see the wee blue circles representing the electrons moving around the circuit. They're going to have a choice here, and we'll see how that affects the overall current, so the overall flow that's being drawn from the battery. Okay, so if you want to do this yourself, if you just click on the junction, a wee pair of scissors should appear. Just do it up here so they're not right next to each other, but there's no difference at all. Just think it looks a wee bit neater. And add it in there. Likewise, you could add it up the top. Remember, it doesn't matter in a series circuit, and there's only one path. Okay, not very neat, but get the idea. So what you should notice on the left-hand side compared to the right is that we've got a decreased current. So the rate that these electrons are moving at is definitely slower than on the right-hand side. And we've added another resistor, so that should kind of make sense then. We know resistors resist that current, that flow of charges. So we've got two 2 ohm resistors. That's actually having the same effect as if we had a single 4 ohm resistor, because the current is having to go through 4 ohms of resistance. And it doesn't really matter if it's a 2 and a 2 or just a 4. Here, if we close the switch, this should already be set up. We've already got the 2 ohm, and then I'm adding a 2 ohm resistor in parallel. So we just keep an eye on this current, see what happens. Okay, so the current has increased this time. But what we know about Ohm's law is that if we have an increased current, we must have a lower resistance. And that's true for this parallel circuit. So adding a resistor in parallel actually decreases the overall resistance of the circuit. If you look at the current just going through one branch, I'll just mention this briefly, I'll get into it a lot more in the next lesson. But if I open and close this switch, but just keep an eye on what's going on here. Okay, so you should have noticed no change. And at this point, remember what we know about voltage in parallel circuits. the voltage across the branch is equal to the supply. So the voltage across this resistor is always 6 volts. The resistance of this resistor is always 2 ohms. So Ohm's law will apply to just this section as well, and the voltage will be equal to the current times the resistance. So the current through that section will be 3 amps. What we do when we add a resistor in parallel, though, is we change that overall resistance of this combination, and it increases the overall current. But like I said, I'll get into that more next time when we look at how we can apply Ohm's law to the circuit as a whole and talk about the current drawn from the battery, or how we can kind of zone in a wee section and say, what about the current at this point, the voltage across this section, and the resistance of this section. So what we've discovered then is adding a resistor in series increases the resistance, which decreases the overall current of the circuit. Adding a resistor in parallel decreases the overall resistance of the circuit, and we know that because we can see that there's an increased current. Because I've made both of these the same value, they're both 2 ohms, I've actually decreased the overall resistance to 1 ohm. If you think about the options that our charges have, although you've added another resistor, you've added another path for the current as well. So thinking back to the traffic analogy, if you had more than one path for the cars to take, you're going to increase the overall flow of traffic. Okay, let's go back to my slides now. And a couple of notes if you do want to take them. I know some of you are taking these in your jotters or bits of paper, or wherever you want to take a note. If not, remember the video is always here if you need to go back and look at it again. Okay, so if we add resistors in series, we're increasing the overall resistance of the circuit. And we can write that as a formula. Probably wouldn't need a formula for this one, but let's see what it looks like anyway, and you'll recognise it in your formula sheet when you come across it. So RT, standing for the total resistance, is R1, which is your first resistance, plus R2, plus R3, plus however many resistors you've got. So for this one, if I was writing out the formula to answer this, which I'll do in the next page, I would only bother writing R1 plus R2 because I've only got 2 resistors here. And I'm sure you can also fill out the answer anyway, but let's just write the work in just to get into the habit of it before things get a bit more complex. Okay, so RT is R1 plus R2. We've just got a 10 and a 10, so it's the same as going through 20 ohms of resistance. And if we add a value for voltage then, we could calculate the current. Okay, adding resistors in parallel, what we said is that decreases the overall resistance of the circuit. Formula for this one looks a bit more complex. Don't let it put you off just yet. Once we look at it with some examples, I'm sure you'll find it's not as daunting as it looks. So we've got 1 over RT, so that just means 1 divided by the total resistance. So we'll have to be careful when we're using this formula that we actually keep going until we've found what we're looking for. The formula is going to help us find 1 over RT. It's not set up just yet to find RT. It's a bit like in maths when you do Pythagoras' theorem and it says x squared equals. And you have to remember at the end, oh, that's x squared. I have to square root to get x. So we'll have to do something similar. It won't be square rooting because that's not a squared, but I'll show you what we do when we get to that stage. So 1 over the total resistance is 1 over, or 1 divided by, the first resistance. And then we keep going for however many branches we've got in our parallel circuit. So for this one, it would just be a 1 over 10 plus 1 over 10. So we have some lovely fractions coming up. Okay, so 1 over RT is 1 over R1 plus 1 over R2. Now you've got options on how you go about this. The maths teacher in me, I'm sure you're all doing National 4 and National 5 maths, and this is something you need to be able to do with a calculator for your National 4 or National 5 maths. If you think I want to stick in my calculator to just make sure I get the right answer, don't do anything silly, then you are always allowed a calculator in physics. So you can have it if you want it. So 1 over 10 plus 1 over 10, well, that would be 2 over 10, which simplifies to 1 over 5. 10th plus a 10th is a 5th. Okay, but that's not our final answer because we've not found total resistance. We've found 1 over the total resistance. So I've got options for you again. In maths, you'll have seen some formulae that look like this. We've got a fraction equal to a fraction. and you might want to cross multiply here. That's absolutely fine. What I would do, which I think is maybe a wee bit simpler, especially for the problems coming up, is just to think, what can I do to that left-hand side to make it just RT? And it's always going to be 1 over RT, which means for every problem, if you imagine flipping that fraction, then you get RT over 1, which just means RT. And from equivalent fractions, if I flip 1, as long as I flip the other one, they're still going to be equivalent. So 1 over RT is 1 over 5. I'd get RT equals 5. 5 over 1 is just 5. So flipping the fractions upside down, I get RT equals 5. Looking back, just check that looks reasonable before we move on actually. We said that adding a resistor in parallel decreases the overall resistance. And this one's like the one I showed you on the FET website, in that we have the same value, of resistor in each branch. So I said the total resistance here was actually 1 ohm, and the total resistance in this one would be 5 ohms, like we've calculated. But that is half the value of the single resistor, because we've added another path. So that's maybe worth remembering that if they are the same value, there's no quicker way of doing this. So when the resistance on each branch is the same, the overall resistance will be that value divided by the number of branches. So for this first example on the left, we've got a 50 and 50. The overall resistance would be 25, just 50 divided by 2. You could, of course, do it the long way. 1 over RT is 1 over R1 plus 1 over R2. You'd have 1 over 50 plus 1 over 50. Well, that'll always give you a 2 on the top, which means your bottom number is going to divide by 2 as well when you simplify that fraction. And then when you flip it, you're always going to have half that number. So there's a wee bit of the maths proof for you, but feel free to do it the long way if you want to do it. You will get the answer 25 ohms. On this one, you'd have 1 over 90 plus 1 over 90 plus 1 over 90, giving you 3 over 90. And when that simplifies down and gets solved, you will end up with 30. So the quick way of doing that is maybe just spotting we've got 90 divided by the 3, because there's 3 branches, and we get 30 ohms. Both looking right, because adding a resistor in parallel has decreased the overall resistance of the circuit. Okay, so let's have a look at when they're not the same value now. We can't just use that kind of quick method. I know that it has to be less than 20, because if that was our circuit, it's got a resistance of 20. So here we've added a resistor in parallel, that has to have decreased that total resistance. But we have to do the long way, so 1 over RT, 1 over R1 plus 1 over R2. The lowest common multiple of 20 and 30, if you're doing this non-calculator, is 60. So you'd have 3 over 60 plus 2 over 60 is 5 over 60. Then we have to solve that. So I've simplified it in my work in here. So 5 over 60 is equal to 1 over 12. You divide both of those numbers by 5. So I want RT on its own. Don't forget this last step, very, very important. We haven't finished yet. That's not RT. It's 1 over RT. So flipping it, RT over 1 would be 12 over 1. So nice and easy when it's a 1 on the top, because anything divided by 1 is just itself. And we get 12 ohms. Said it needed to be less than 20. It's less than 20. Sounds good. Okay, just want to do a couple of examples now where we've got a combination of different things going on in our circuit. So here we've got a 10 ohm resistor, and then we have this parallel section. So to answer this, you might want to redraw the circuit, but draw a simplified version of it. So you might think, right, that looks a wee bit complicated. I know a 10 is in series because it has to go through the 10 and then it has to go through this big thing, but it has an option here. So to make this simpler, think, well, what would this section be the same as? What is a 20 and a 10 in parallel the same as having resistance-wise? I know it has to be less than 10, because adding that 20 in parallel to it has to have decreased the resistance of this section. But what I really want to think is, if I could replace this with a single resistor, what would the equivalent resistance be? So the first thing we need to work out is the resistance of that parallel section. So feel free to pause the video if you want to have a go yourself. We're looking at 1 over 20 plus 1 over 10. which is 1 over 20 plus 2 over 20, which is 3 over 20. So solving that for RT, you should get 6.67. You might have rounded differently, you might have 6.7 or something like that. It's absolutely fine. Okay, so like I was saying, that would be the same as replacing that section. So I just want to do that just now. This might be a bit messy with me writing on my screen, so just bear with me. Same as taking out that section and saying, well, we've just worked out that the resistance of that section is equal. That's ambitious. I'm going to fit it in there to 6.67 ohms. That would have the same effect on the current because we just worked out that is the resistance of that section. So now we can see maybe a bit more clearly that we've got a 10 ohm in series with 6.67 ohms. Series was the easy one, remember? It has to go through the 10. It has to go through 6.67 ohms of resistance, whether that was as a parallel section that we've calculated earlier, or whether it's a single resistor of 6.67. Connect the series. We have to go through the 10 and the 6.67, so the total resistance is this. I like to write total resistance in my final step because otherwise you've got a few things going on in these problems that say RT, which stands for total resistance. So I just think that can maybe get a wee bit confusing if your layout's not really clear. Because someone, when you're looking at your work, might say, well, what is the total resistance? You've got RT over here, over here. So I think by labelling my sections and writing total resistance for my final total, double underline, it's nice and obvious. Okay, we're going to do 2 more of these. So this one here, again, we've got some things in series, some things in parallel. Now think about what the current's having to do. On this top branch, it goes through 100 and goes through another 100. That means they're in series with each other. And collectively, the 50, or collectively they are in parallel with the 50 ohm resistor. So to simplify this one, what I might want to do is think, what is my 100 and my 100 next to each other equivalent to? Just rub that out and back with my pen. So I want to replace that 100 and that 100 with a single resistor. Well, the current would have to go through both. They were in series, so that is going to be a 200 ohm resistance. Of course, you can write out the working like this. So now that I've simplified it a bit, you can see, okay, the current then has this option. We've got a 200 ohm or a 50 ohm there in parallel, so I have to use my formula, 1 over RT, so 1 over R1 plus 1 over R2. Again, remember you can pause it if you want some time to work it out yourself. Simplifying that down, I would get 1 over 200 plus 4 over 200, which is 5 over 200, which simplifies to 1 over 40. RT on its own would be 40 over 1, or 40 ohms. Smaller than the smallest resistance, which is what we expect. Total resistance, nice obvious answer, 40 ohms. Okay, final one. So the layout of this maybe makes it look a little bit trickier to spot how that 1 kilo ohm resistor is connected in relation to these other two. You can definitely see this split, so we should be recognising that there's some kind of parallel section in this circuit. If we imagine this current, then we've got this 1 kilo ohm that we have no option but to go through, and then the choice, so then this parallel section. So 1 kilo ohm is actually in series with this section here. If you want to redraw this circuit to one you're maybe more familiar with, what we could have is, again, excuse the messy diagrams, I could have the bend. Remember, this is just wire, so it doesn't matter where I put the resistor in this wire. So I could have the bend first and then the 1 kilo ohm resistor. And then what happens after the 1 kilo ohm resistor is the split. But I could draw that with the wires slightly differently. But now it looks perhaps a bit more familiar to you. And that's each of the 500 ohm resistors. So to simplify this one, I want to know, well, what's the resistance of that section, because the 1 kilo ohm is in series with that as a resistor or resistance. So the simplest way for this is to work out what's the resistance of that section. And the reason I've got such a small piece of work in for this is because they're both 500 ohm resistors. So if we think back to what we said earlier, if they're the same value in parallel, it's actually nice and easy, if you remember, that we can just do 500 divided by the number of branches, which was 2. So we've got 250 ohms of resistance there, and the 1 kilo ohm in series with that. That gives you a total resistance of 1,250 ohms, or 1.25 kilo ohms. Okay, watch out for the kilo, meaning 1,000 ohms, or 1 times 10 to the 3 ohms. Make an answer nice and clear. Okay, really quick recap then, what we've discovered today. If you add them in series, that increases the total resistance of the circuit, and this is the formula that would help us calculate that. Adding them in parallel actually decreases the overall resistance of the circuit. Next time we're going to be looking at what I touched on briefly, which is how you apply Ohm's law to these circuits, how you can look at the current as a whole that's been drawn from the battery using that overall voltage and that overall resistance, and how you can zone in individual parts of the circuit and think, well, what would the current through this section be based on the voltage across and the resistance of that section. Okay, see you next time.